The planet Mercury. This is an article from Wikipedia, the Free Encyclopedia, read by Thomas Eckerle on the 16th of January 2008. Mercury is the innermost and smallest planet in the solar system, orbiting the Sun once every 88 days. It ranges in brightness from about -2.0 to 5.5 in apparent magnitude, but is not easily seen as its greatest angular separation from the Sun is only 28.3 degrees. It can only be seen in the morning or evening twilight. Comparatively little is known about the planet. The only spacecraft to approach Mercury was Mariner 10 from 1974 to 1975, which mapped only 40 to 45% of the planet's surface. However, on January 14, 2008, the Messenger spacecraft began making several passes by Mercury, which will culminate in an orbital insertion in 2011. It will completely survey and map the planet. Physically, Mercury is similar in appearance to the Moon, as it is heavily cratered and has no natural satellites and no substantial atmosphere. The planet has a large iron core, which generates a magnetic field about 1% as strong as that of the Earth. Surface temperatures on Mercury range from about 90 to 700 Kelvin. That's -180 to 430 degrees Celsius, with the subsolar point being the hottest and the bottoms of craters near the poles being the coldest. Recorded observations of Mercury date back to the time of the Sumerians in the 3rd millennium BC. The Romans named the planet after the Roman god Mercurius, equated to the Greek Hermes and the Babylonian Nabu. The astronomical symbol for Mercury is a stylized version of the god's head and winged hat atop his caduceus, an ancient astrological symbol. The Greeks of Hesiod's time called it Stilbon, the gleaming, and Hermaon. Before the 5th century BC, Greek astronomers believed the planet to be two separate objects, one visible only at sunrise, the other only at sunset. In India, the planet was named Buddha, after the son of Chandra, the moon. The Chinese, Korean, Japanese, and Vietnamese cultures referred to the planet as the water star, based on the 5 elements. The Hebrews named it Kohav Hama, the star of the hot one being the sun. Mercury is smaller, though still having a greater mass, than the biggest of the natural satellites in our solar system, Ganymede and Titan. Contents: 1. Internal structure. 2. Surface geology. 3. Atmosphere. 4. Magnetosphere. 5. Orbit and rotation. 5.1. Advance of perihelion. 5.2. Spin-orbit resonance. 6. Observation. 7. Studies of Mercury. 7.1. Ancient astronomers. 7.2. Ground-based telescopic research. 7.3. Research with space probes. 7.3.1. Mariner 10. 7.3.2. Messenger. 7.3.3. Bepi Colombo. 8. See also. 1. Internal structure. Mercury is one of the 4 terrestrial planets, being a rocky body like the Earth. It is the smallest of the 4, with a diameter of 4,879 kilometers at its equator. Mercury consists of approximately 70% metallic and 30% silicate material. The density of the planet is the second highest in the solar system at 5.43 grams per cubic centimeter, only slightly less than Earth's density. If the effect of gravitational compression were to be factored out, the materials of which Mercury is made would be denser, with an uncompressed density of 5.3 grams per cubic centimeter versus Earth's 4.4 grams per cubic centimeter. Mercury's density can be used to infer details of its inner structure. While the Earth's high density results appreciably from gravitational compression, particularly at the core, Mercury is much smaller, and its inner regions are not nearly as strongly compressed. Therefore, for it to have such a high density, its core must be large and rich in iron. Geologists estimate that Mercury's core occupies about 42% of its volume. For Earth, this proportion is 17%. Recent research strongly suggests Mercury has a molten core. Surrounding the core is a 600-kilometer mantle. It is generally thought that early in Mercury's history, a giant impact with a body several hundred kilometers across stripped the planet of much of its original mantle material, resulting in the relatively thin mantle compared to the sizable core. Alternative theories are discussed below. Mercury's crust is thought to be 100 to 200 kilometers thick. One distinctive feature of Mercury's surface are numerous narrow ridges, some extending over several hundred kilometers. It is believed that these were formed as Mercury's core and mantle cooled and contracted at a time when the crust had already solidified. Mercury has a higher iron content than any other major planet in our solar system, and several theories have been proposed to explain this. The most widely accepted theory is that Mercury originally had a metal-silicate ratio similar to common chondrite meteors, thought to be typical of average solar system rocky matter, and a mass approximately 2.25 times its current mass. However, early in the solar system's history, Mercury was struck by a planetesimal of approximately 1/6 that mass. The impact would have stripped away much of the original crust and mantle, leaving the core behind as a relatively major component. A similar process has been proposed to explain the formation of Earth's moon, see giant impact theory. Alternatively, Mercury may have formed from the solar nebula before the Sun's energy output had stabilized. The planet would initially have had twice its present mass, but as the protosun contracted, temperatures near Mercury could have been between 2500 and 3500 Kelvin, and possibly even as high as 10,000 Kelvin. Much of Mercury's surface rock could have been vaporized at such temperatures, forming an atmosphere of rock vapor, which could have been carried away by the solar wind. A third theory proposes that the solar nebula caused a drag on the particles from which Mercury was accreting, which meant that lighter particles were lost from the accreting material. Each of these theories predicts a different surface composition, and two upcoming space missions, Messenger and Bepi Colombo, both aim to take observations that will allow the theories to be tested. 2. Surface geology. Mercury's surface is overall very similar in appearance to that of the Moon, showing extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. Since our knowledge of Mercury's geology is based on only a single spacecraft flyby, it is the least well understood of the terrestrial planets. Surface features are given the following names: albedo features, areas of markedly different reflectivity; dosa, ridges; montes, mountains; planetea, plains; rupes, scarps; valles, valleys. Mercury was heavily bombarded by comets and asteroids during and shortly following its formation 4.6 billion years ago, as well as during a possibly separate subsequent episode called the Late Heavy Bombardment that came to an end 3.8 billion years ago. During this period of intense crater formation, the planet received impacts over its entire surface, facilitated by the lack of any atmosphere to slow impactors down. During this time, the planet was volcanically active. Basins, such as the Caloris Basin, were filled by magma from within the planet, which produced smooth plains similar to the maria found on the Moon. Craters on Mercury range in diameter from a few meters to hundreds of kilometers across. The largest known craters are the enormous Calorus Basin with a wide diameter of 1300 kilometers, and the Skinnakas Basin with a diameter of 1600 kilometers, but known only from low-resolution Earth-based imaging of the non-Mariner imaged hemisphere. The impact which created the Calorus Basin was so powerful that it caused lava eruptions and left a concentric ring over 2 kilometers tall surrounding the impact crater. At the antipode of the Calorus Basin is a large region of unusual hilly terrain known as the weird terrain. One hypothesis for the origin of this geomorphological unit is that shock waves generated during the impact traveled around the planet, and when they converged at the basin's antipode, 180 degrees away, the high stresses were capable of fracturing the surface. Alternatively, it has been suggested that this terrain formed as a result of the convergence of ejecta at this basin's antipode. The plains of Mercury have 2 distinct ages. The younger plains are less heavily cratered and probably formed when lava flows buried earlier terrain. One unusual feature of the planet's surface is the numerous compression folds which crisscross the plains. It is thought that as the planet's interior cooled, it contracted and its surface began to deform. The folds can be seen on top of other features such as craters and smoother plains, indicating that they are more recent. Mercury's surface is also flexed by significant tidal bulges raised by the Sun. The Sun's tides on Mercury are about 17% stronger than the Moon's on Earth. Like the Moon, the surface of Mercury has likely incurred the effects of space weathering process. Solar wind and micrometeorite impacts can darken the albedo and alter the reflectance properties of the surface. The mean surface temperature of Mercury is 452 Kelvin. That's 179 degrees Celsius. But it ranges from 90 Kelvin, minus 183 Celsius, to 700 Kelvin, 427 Celsius, due to the absence of an atmosphere. The sunlight on Mercury's surface is 6.5 times as intense as it is on Earth, with a solar constant value of 9.13 kilowatts per square meter. Despite the generally extremely high temperature of its surface, observations strongly suggest that ice exists on Mercury. The floors of some of the deep craters near the poles are never exposed to direct sunlight, and temperatures there remain far lower than the global average. Water ice strongly reflects radar, and observations reveal that there are patches of very high radar reflection near the poles. While ice is not the only possible cause of these reflective regions, astronomers believe it is the most likely. The icy regions are believed to be covered to a depth of only a few meters, and can contain about 10 to the 14th to 10 to the 15th kilograms of ice. By comparison, the Antarctic ice sheet on Earth has a mass of about 4 times 10 to the power of 18 kilograms, and Mars's south polar caps contain about 10 to the 16th kilograms of water. The origin of the ice on Mercury is not yet known, but the 2 most likely sources are from outgassing of water from the planet's interior or deposition by impacts of comets. 3. Atmosphere. Mercury is too small for its gravity to retain any significant atmosphere over long periods of time. However, it does have a tenuous atmosphere containing hydrogen, helium, oxygen, sodium, calcium, and potassium. This atmosphere is not stable. Atoms are continuously lost and replenished from a variety of sources. Hydrogen and helium atoms probably come from the solar wind diffusing into Mercury's magnetosphere before later escaping back into space. Radioactive decay of elements within Mercury's crust is another source of helium, as well as sodium and potassium. Water vapor is probably present, being brought to Mercury by comets impacting on its surface. 4. Magnetosphere. Despite its slow 59-day-long rotation, Mercury has a relatively strong and apparently global magnetic field. It is about 1.1% as strong as the Earth's. It is likely that this magnetic field is generated in a manner similar to Earth's by a dynamo of circulating liquid core material. A mechanism that has been suggested for keeping it liquid are particularly strong tidal effects during periods of high orbital eccentricity. Mercury's magnetic field is strong enough to deflect the solar wind around the planet, creating a magnetosphere, inside which the solar wind does not penetrate. This is in contrast to the situation on the Moon, which has a magnetic field too weak to stop the solar wind impacting on its surface, and so lacks a magnetosphere. 5. Orbit and rotation. The orbit of Mercury is the most eccentric of the major planets, with the planets distant from the Sun ranging from 46 million to 70 million kilometers. It takes 88 days to complete an orbit. A diagram illustrates the effects of the eccentricity, showing Mercury's orbit overlain with the circular orbit having the same semi-major axis. The higher velocity of the planet when it is near the perihelion is clear from the greater distance it covers in each 5-day interval. The size of the spheres, inversely proportional to the distance from the Sun, is used to illustrate the varying heliocentric distance. This varying distance to the Sun, combined with a 3:2 spin-orbit resonance of the planet's rotation around its axis, result in a complex variations of the surface temperature. Mercury's orbit is inclined by 7 degrees to the plane of Earth's orbit, the ecliptic, as shown in a diagram. As a result, transits of Mercury across the face of the Sun can only occur when the planet is crossing the plane of the ecliptic at the time it lies between the Earth and the Sun. This occurs about every 7 years on average. Mercury's actual tilt is only 0.01 degrees. This is over 300 times smaller than that of Jupiter, which is the second smallest actual tilt of all planets at 3.1 degrees. This means an observer at Mercury's equator during local noon would never see the Sun more than 1/100th of 1 degree north or south of the zenith. Conversely, at the poles, the Sun never rises more than 0.01 degrees above the horizon. At certain points on Mercury's surface, an observer would be able to see the Sun rise about halfway, then reverse and set before rising again, all within the same Mercurian day. This is because approximately 4 days prior to perihelion, Mercury's angular orbital velocity exactly equals its angular rotational velocity, so that the Sun's apparent motion ceases. At perihelion, Mercury's angular orbital velocity then exceeds the angular rotational velocity. Thus, the Sun appears to move in a retrograde direction. 4 days after perihelion, the Sun's normal apparent motion resumes at these points. 5.1 Advance of perihelion. It was noticed in the 19th century that the slow precession of Mercury's orbit around the Sun could not be completely explained by Newtonian mechanics, and perturbations by the known planets, notably by the French mathematician Leverrier. It was hypothesized that another planet might exist in an orbit even closer to the Sun to account for this perturbation. Other explanations considered including a slight oblateness of the Sun. The success of the search for Neptune based on its perturbations of the orbit of Uranus, led astronomers to place great faith in this explanation. And the hypothetical planet was even named Vulcan. However, in the early 20th century, Albert Einstein's general theory of relativity provided the explanation for the observed precessions. The effect is very small. The Mercurian relativistic perihelion advance excess is just 42.98 arcseconds per century. Therefore, it requires a little over 12 million orbits for a full excess turn. Similar but much smaller effects operate for other planets, being 8.62 arcseconds per century for Venus, 3.84 for Earth, 1.35 for Mars, and 10.05 for 1566 Icarus. 5.2 Spin-orbit resonance. For many years, it was thought that Mercury was synchronously tightly locked with the Sun, rotating once for each orbit and keeping the same face directed towards the Sun at all times, in the same way that the same side of the Moon always faces the Earth. However, radar observations in 1965 proved that the planet has a 3:2 spin-orbit resonance, rotating 3 times for every 2 revolutions around the Sun. The eccentricity of Mercury's orbit makes this resonance stable at perihelion, when the solar tide is strongest. The Sun is nearly still in Mercury's sky. The original reason astronomers thought it was synchronously locked was that whenever Mercury was best placed for observation, it was always at the same point in its 3:2 resonance, hence showing the same face. Due to Mercury's 3:2 spin-orbit resonance, a solar day, the length between 2 meridian transits of the Sun, lasts about 176 Earth days. A sidereal day, the period of rotation, lasts about 58.7 Earth days. Orbital simulations indicate that the eccentricity of Mercury's orbit varies chaotically from 0, circular, to a very high 0.47 over millions of years. This is thought to explain Mercury's 3:2 spin-orbit resonance, rather than the more usual 1:1, since this state is more likely to arise during a period of high eccentricity. 6. Observation. Mercury's apparent magnitude varies between about -2, brighter than Sirius, and 5.5. Observation of Mercury is complicated by its proximity to the Sun, as it is lost in the Sun's glare for much of the time. Mercury can be observed for only a brief period during either morning or evening twilight. The Hubble Space Telescope cannot observe Mercury at all, due to safety procedures which prevent its pointing too close to the Sun. Like the Moon, Mercury exhibits phases seen from Earth, being new at inferior conjunction and full at superior conjunction. The planet is rendered invisible on both of these occasions, by virtue of its rising and setting in concert with the Sun in each case. The first and last quarter phases occur at the greatest elongation east and west, respectively, when Mercury's separation from the Sun ranges anywhere from 18.5 degrees at perihelion to 28.3 degrees at aphelion. At greatest elongation west, Mercury rises earliest before the Sun, and at greatest elongation east, it sets latest after the Sun. Mercury attains inferior conjunction every 116 days on average, but this interval can range from 111 days to 121 days due to the planet's eccentric orbit. Its period of retrograde motion, as seen from the Earth, can vary from 8 to 15 days on either side of inferior conjunction. This large range also arises from the planet's high orbital eccentricity. Mercury is more often visible from Earth's southern hemisphere than from its northern hemisphere. This is because its maximum possible elongations west of the Sun always occur when it is early autumn in the southern hemisphere, while its maximum possible eastern elongations happen when the southern hemisphere is having its late winter season. In both these cases, the angle Mercury strikes with the ecliptic is maximized, allowing it to rise several hours before the Sun in the former instance and not set until several hours after sundown in the latter, in countries located at the southern temperate zone latitudes such as Argentina and New Zealand. By contrast, at northern temperature latitudes, Mercury is never above the horizon of a more or less fully dark night sky. Mercury can, like several other planets and the brighter stars, be seen during a total solar eclipse. Mercury is brightest as seen from the Earth when it is at a gibbous phase, between either quarter phase and full. Although the planet is further away from the Earth when it is gibbous than when it is a crescent, the greater illuminated area visible more than compensates for the greater distance. The opposite is true for Venus, which appears brightest when it is a thin crescent because it is much closer to Earth than when gibbous. 7. Studies of Mercury. 7.1. Ancient astronomers. The earliest mentions of Mercury come from the 3rd millennium BC, when it was known to the Sumerians of Mesopotamia as Ubu Idim Gud-Ud, among other names. The Babylonians, 2000 to 500 BC, succeeded the Sumerians, and early Babylonians may have recorded observations of the planet, although these have not survived. Later Babylonian records from the 7th century BC refer to much earlier records. The Babylonians called the planet Nabu, or Nebu, after the messenger to the gods in their mythology. The ancient Greeks gave the planet two names: Apollo when it was visible in the morning sky, and Hermes when visible in the evening. However, Greek astronomers came to understand that two names referred to the same body, with Pythagoras being the first Greek to propose the idea. 7.2. Ground-based telescopic research. The first telescopic observations of Mercury were made by Galileo in the early 17th century. Although he observed phases when he looked at Venus, his telescope was not powerful enough to see the phases of Mercury. In 1631, Pierre Gassendi made the first observations of the transit of a planet across the Sun when he saw a transit of Mercury predicted by Johannes Kepler. In 1639, Giovanni Zuppi used a telescope to discover that the planet had orbital phases similar to Venus and the Moon. The observation demonstrated conclusively that Mercury orbited around the Sun. A very rare event in astronomy is the passage of one planet in front of another, occultation, as seen from the Earth. Mercury and Venus occulted each other every few centuries, and the event of the 28th of May 1737 is the only one historically observed, having been seen by John Bevis at the Royal Greenwich Observatory. The next occultation of Mercury by Venus will be in 2133. The difficulties inherent in observing Mercury meant that it has been far less studied than the other planets. In 1800, Johann Schröter made observations of surface features, but erroneously estimated the planet's rotational period at about 24 hours. In the 1880s, Giovanni Schiaparelli mapped the planet more accurately and suggested that Mercury's rotational period was 88 days, the same as its orbital period due to tidal locking. This phenomenon is known as synchronous rotation and is also shown by the Earth's moon. The theory that Mercury's rotation was synchronous became widely held, and it was a significant shock to astronomers when radio observations made in the 1960s questioned this. If Mercury were tidally locked, its dark phase would be extremely cold, but measurements of radio emissions revealed that it was much hotter than expected. Astronomers were reluctant to drop the synchronous rotation theory and proposed alternative mechanisms such as a powerful heat-distributing winds to explain the observations. In June 1962, Soviet scientists at the Institute of Radio Engineering and Electronics of the USSR Academy of Sciences, led by Vladimir Kotelnikov, became first to bounce radar signals of Mercury and receive it, starting radar observations of the planet. 3 years later, observations by Americans Gordon Pettengill and R. Dice using 300-meter Arecibo Observatory radio telescope in Puerto Rico showed conclusively that the planet's rotational period was about 59 days. Italian astronomer Giuseppe Colombo noted that this value was about 2/3 of Mercury's orbital period, and proposed that a different form of tidal locking had occurred in which the planet's orbital and rotational periods were locked in a 3:2 rather than a 1:1 resonance. Data from Mariner 10 subsequently confirmed this view. Ground-based observations did not shed much further light on the innermost planet, and it was not until space probes visited Mercury that many of its fundamental properties became known. However, recent technological advances have led to improved ground-based observations. In 2000, high-resolution Lockheed imaging from the Mount Wilson Observatory 1500mm telescope provided the first views that resolved some surface features on the parts of Mercury which were not imaged in the Mariner missions. Later imaging has shown evidence of a huge double-ringed impact basin, even larger than the Caloris basin, in the non-Mariner imaged hemisphere. It has informally been dubbed the Skinarkas basin. Most of the planet has been mapped by the Arecibo radio telescope with 5-kilometer resolution, including polar deposits in shallow craters of what may be water ice. Ground-based telescopes have detected the bright rays around some radar-mapped craters. 7.3 Research with space probes. Reaching Mercury from Earth poses significant technical challenges, since the planet orbits so much closer to the Sun than does the Earth. A Mercury-bound spacecraft launched from Earth must travel over 91 million kilometers into the Sun's gravitational potential well, starting from the Earth's orbital speed of 30 kilometers per second. The change in velocity, delta V, the spacecraft must make to enter into a Hoffman transfer orbit that passes near Mercury is large compared to other planetary missions. The potential energy liberated by moving down the Sun's potential well becomes kinetic energy, requiring another large delta V to do anything other than rapidly pass by Mercury. In order to land safely or enter stable orbit, the spacecraft must rely entirely on rocket motors, since aerobraking is ruled out because the planet has very little atmosphere. A trip to Mercury actually requires more rocket fuel than that required to escape the solar system completely. As a result, only 2 space probes have visited the planet so far. 7.3.1 Mariner 10. The first spacecraft to approach Mercury was NASA's Mariner 10, 1974-75. The spacecraft used the gravity of Venus to adjust its orbital velocity so that it could approach Mercury, the first spacecraft to use this gravitational slingshot effect. Mariner 10 provided the first close-up images of Mercury's surface, which immediately showed its heavily cratered nature, and also revealed many other types of geological features, such as the giant scarps, which were later ascribed to the effect of the planet shrinking slightly as its iron core cools. Unfortunately, because Mariner 10's orbital period was almost exactly 3 sidereal Mercury days, the same face of the planet was lit at each of Mariner 10's close approaches, resulting in less than 45% of the planet's surface being mapped. The spacecraft made 3 close approaches to Mercury, the closest of which took it to within 327 kilometers of the surface. At the first close approach, instruments detected a magnetic field to the great surprise of planetary geologists. Mercury's rotation was expected to be much too slow to generate a significant dynamo effect. The second close approach was primarily used for imaging, but at the third approach extensive magnetic data were obtained. The data revealed that the planet's magnetic field is much like the Earth's, which deflects solar wind around the planet. However, the origin of Mercury's magnetic field is still the subject of several competing theories. Just a few days after its final close approach, Mariner 10 ran out of fuel. Since its orbit could no longer be accurately controlled, mission controllers instructed the probe to shut itself down. Mariner 10 is thought to be still orbiting the Sun, passing close to Mercury every few months. 7.3.2 Messenger. A second NASA mission to Mercury named Messenger, Mercury Surface Space Environment Geochemistry and Ranging, was launched on the 3rd of August 2004 from the Cape Canaveral Air Force Station aboard a Boeing Delta II rocket. The Messenger spacecraft will make several close approaches to planets to place it onto the correct trajectory to reach an orbit around Mercury. It made a flyby of the Earth in August 2005 and of Venus in October 2006 and June 2007. The first flyby of Mercury occurred on January the 14th, 2008. 2 more flybys of Mercury are scheduled in October 2008 and September 2009. Most of the hemisphere not imaged by Mariner 10 will be mapped during the flybys. The probe will then enter an elliptical orbit around the planet in March 2011. The nominal mapping mission is 1 terrestrial year. Orbital periapsis will be over the northern hemisphere. Communications with Earth occur near apoapsis every 12 hours. The mission is designed to shed light on 6 key issues: Mercury's high density, its geological history, the nature of its magnetic field, the structure of its core, whether it really has ice at its poles, and where its tenuous atmosphere comes from. To this end, the probe is carrying imaging devices which will gather much higher resolution images of much more of the planet than Mariner 10, assorted spectrometers to determine abundances of elements in the crust, and magnetometers and devices to measure velocities of charged particles. Detailed measurements of tiny changes in the probe's velocity as it orbits will be used to infer details of the planet's interior structure. 7.3.3 Bepi Colombo. The European Space Agency is planning a joint mission with Japan called Bepi Colombo, which will orbit Mercury with 2 probes, one to map the planet and the other to study its magnetosphere. An original plan to include a lander has been shelved. A Russian Soyuz rocket will launch the bus carrying the 2 probes in 2013 from ESA's Guyana Space Center to take advantage of its equatorial location. As with Messenger, the Bepi Colombo bus will make close approaches to other planets en route to Mercury for orbit-changing gravitational assists. Passing the Moon and Venus and making several approaches to Mercury before entering orbit, a combination of chemical and ion engines will be used, the latter thrusting continuously for long intervals. The spacecraft bus will reach Mercury in 2019. The bus will release the magnetometer probe into an elliptical orbit, then chemical rockets will fire to deposit the mapper probe into a circular orbit. Both probes will operate for a terrestrial year. The mapper probe will carry an array of spectrometers similar to those on Messenger, and will study the planet at many different wavelengths, including infrared, ultraviolet, X-ray, and gamma ray. Apart from intensively studying the planet itself, mission planners also hope to use the probe's proximity to the Sun to test the predictions of general relativity theory with improved accuracy. The mission is named after Giuseppe Bepi Colombo, the scientist who first determined the nature of Mercury's spin-orbit resonance and who was also involved in the planning of Mariner 10's gravity-assisted trajectory to the planet in 1974. See also Mercury in fiction, colonization of Mercury, and exploration of Mercury. This article includes references for further study. The text is available under the terms of the GNU Free Documentation License. This sound file is considered a derivative work and is also released under the GNU Free Documentation License.